both a ratio test and root test are based on comparison with the geometric series. And so this is explaining why the geometric series is so crucial. Okay, so what is the ratio test? Well, the ratio test is simply the test that if you're looking at, so if you have a series, you don't have to look at any other series. Like in the comparison test, you had to find another series. But in the ratio test, so this is a ratio test, so you're looking at a series like this. And the ratio test is that you're looking at an plus 1 over an. So you are looking at the ratio between two consecutive elements of the ans. Right? So you're looking at this. And you're looking at the absolute value of this. And you're asking if the limit here as n goes to infinity, suppose that the limit exists, and let's say that the limit is a. So it's asking you if this, it's somehow the test here, this form of the ratio test, it requires that the ratio here has a limit. So the ratio test then say that if a here is if a here is right, sorry, yeah, if a here is less than 1, then the series is, so let me write it like this. So a less than 1, this here means that the series is convergent. True, if this a here is bigger than 1, this implies that the series is divergent. And 3 is that if this a here is 1, then the test is inconclusive. But so it's important to remember that it is possible that you don't get anything out of the test. Okay, if you are in the unlucky case where this limit is 1. Right? And it is, I should also emphasize that it is crucial to have a limit. Right? So the test here in this form, it's crucial to have a limit. Okay. And we'll talk a little bit, and we'll come back to that, because we'll come back to this. Okay, so now let me try to explain why you have, well, in conclusive, I don't really need to explain anything, right? But why in the case, so proof of case 1. So this means that I have to show, so need to show that if this limit of an plus 1 over an, if this here is less than 1, then the series is convergent. And I'll just sketch the proof because we're going to do, yeah, I will just sketch the proof. We sort of come back in a way to the proof because it's very close to the same proof that is used in the case of the root test. So that's what I need. So I have that there exists, so given A0 less than 1, so given A0 with A0 bigger than this A and less than 1. Right, so if you pick A0 that is strictly bigger than A and still less than 1, then we know that there exist n such that if little n is bigger than this capital N, then an plus 1 over an, and really I should have absolute value here on this. Then we have that this thing here is less than, it's less than A0, right? Because if you're very far out, then this ratio is going to be very close to this, but this is strictly less than that, right? So we have this, right? Okay, so this means that maybe I shouldn't call it A0 because there's too many A's now. Let's call it something else. Let's call it alpha to make it just look much more distinct. Okay, so this means that, so you see that in other words, if n here is bigger than this capital N, then you have just multiplying over, you have that an plus 1 is less than alpha times an, like that, right? In the ratio test, I should have said that, but obviously you are assuming that these ANs are not 0, so you can divide by them. Right? So you have this. If you're far out, you have this, that the next one is a fraction of the previous one, right? But this means, of course, that if you're looking at n is bigger or equal to this capital N, well, you have that A capital N plus 1, right? If you're using this A capital N as little n, then you have that this thing here, this is now this here is now, sorry, if you first pick n equal to capital N, then what does this inequality tell you? It tells you that A capital N plus 1 is less or equal to alpha A capital N. Now apply this inequality here for n plus capital N plus 1. So then you have that A capital N plus 2 absolute value is less or equal to alpha an plus 1, like that, right? But you already proven that this thing here, forget about the alpha here, but you've proven this inequality. So filling in that inequality, I have this alpha here, but then I have another alpha that is this, and then like this, right? And so now you can continue this way. So this here is like alpha squared times A capital N. And so now you see that you can continue. So if you're looking at, if you continue like this, then you see that A capital N plus some little m is less or equal to alpha to the power m. times a to absolute value of an, right? This here, the previous line was just where m was equal to 2, but you really get it for all integers, right? And so this say that at least the tail of this sequence here, the tail of the an sequence, this is just some fixed constant. This here is a convergent geometric series. So the tail is bounded by a convergent geometric series. So you can just apply the first comparison test to prove that the sequence A, that the series AN is actually convergent. Okay, so the ratio test again was to compare it, use the first comparison test, where the comparison was the geometric series. Okay. And so, of course, this prove 1, 2 here, but 2 is kind of really the same, because if this alpha here, so to show the second part, again, the third one, to prove it's inconclusive, there's nothing to prove, because it leaves open any possibility. But you want to show that if this limit here, so if this limit, so proof of 2, we're assuming that A here is bigger than 1, but this means that there exists, so if you take alpha, so this time choose alpha such that alpha is bigger than 1, but it's smaller than A. But then you have that for, right, since this ratio is converging for little n bigger than, there exists some capital N, so that if this little n is bigger than a capital N, then you have that an plus 1 over an, that this thing here, if it's far enough out, it's going to converge here, but at least far enough out, it's going to be bigger than alpha, right? Multiplying over again means that an plus 1 is bigger than alpha times an. This here is now bigger than 1. And so in the same way as before, you see that if you're far enough out, then the next element is some multiple, some big number, some at least bigger than 1, times the previous one, right? But this means that they're getting larger and larger as you know, from some fixed stage on and outward, the ANs are getting larger and larger. So they don't converge to 0 as they were supposed to, right? So this is proving true, right? And 3 again, there's nothing to prove because it leaves open both possibilities. Okay.
I have a question about the first proof.
Yeah.
Does that assume that the series is monotone decreasing?
Sorry.
Because we're, like, I guess just looking at it, like from a high level, we're saying that A of n plus 1 over A of n.
Wait. So you're asking, what are you asking?
So for part 1, when we say that A is less than 1, that implies that it converges.
Yep.
Is that only going to work for monotone decreasing?
No. So there's no assumption here on whether the sequence is right. I mean, so one implies that the absolute value is going down, as you say, right? Yeah. But it could alternate signs and things like that. Yeah. But it is yeah. And so it's just because you're comparing it with, you're going to compare it with a convergent geometric series. And in convergent geometric series, the next element is some fixed fraction of the previous one. Yeah. So you're right that in order for the ratio test to give you convergence, then it's going to require that sufficiently far out the absolute value of the AN element is going down. Right? Yep. So the other, and this is like, and this in a way addresses that point you're making there. So the other test that is also based on comparing it with the geometric series, but this does not compare consecutive elements. So it's leaving the possibility that the next element could be larger than the previous. And so this is the root test. But of course, it cannot be that you cannot keep having the next element larger than the previous, right? But you could have, there could be somewhere where, the next one actually went up, but then presumably after that, they're going down at least for a long time, and then maybe there's another one that jumps up, but not very much, etc. Right? And the root test is okay with that, whereas that test wasn't okay with that. So the root test, so you have a series again, like this. And the root test is that you're taking the absolute value of this, and then you're taking the nth root. So this means this is the same as saying AN absolute value, if you want to write it like this, 1 over n. Right. So it's dealing with this, and the root test is saying that suppose that these, when you form this here, that this has a limit. Suppose that this nth root, suppose that this here has a limit, and let's call this limit C. Suppose that you have this. Then it has the same 3 parts here as in the previous. And so this is, so there's 3 possibilities where C here is less than 1, then this implies that the series is convergent. Two, C is bigger than 1, implies that the series is divergent. And again, the case where C here is equal to 1 in conclusion. Test is in conclusion. And again, we're going to compare with the geometric series. So let's see how the proof works. So okay, so now let's prove 1. Proof of 1. So again, we are in a situation where we have that the nth root of the absolute value here, as n goes to infinity, is equal to some c, and we're assuming that the c is less than 1. Right? So now I'm again choosing something that is between c and 1. So choose c. So let's call it c0 with c less than c0 less than 1. Okay. And now we know that because we have this limit, we know that there exists a capital N such that if little n is bigger than capital N, then the nth root of this absolute value sign is actually less or equal to C0, right? This is just because C0 was strictly bigger than C, right? So we have that. So now we just take the nth power on both sides. So this implies by taking n power, the nth power we get that A absolute value of AN, is less or equal to C0 to the power n, okay? Right, so, but that's already great, right? Because this means that you have compared, at least from a certain stage and outward, you have compared the AN with, if you're thinking about that this thing here is like the BN, right? Then you have compared this guys here with this series here based on these, at least from this capital N and outward. And this is a geometric series because it's just some number strictly smaller than 1 multiplied by itself n times. So again, by the first comparison test, the AN is convergent, right? So and note here that what you're proving is you're actually proving that this series here is convergent, right? Right? Because you're comparing this series here with a geometric series, but this here is just means that the original series here was absolutely convergent. But absolute convergence implies convergence, right? So you are actually proving absolute convergence. Okay. Now let's try to, again, there's these 3 parts to it, but the last one leaves open any possibility, so there's nothing to prove. So let's just prove the second part here, and that's just goes similarly. And again, it fails dramatically to be convergent because the AN, as we will see, does not actually go to 0. So proof of 2. So we have that this. So we're assuming that this thing here, this here converge to some C here, which is now bigger than 1. So this means that there exist. Capital N such that if little n is bigger than this capital N, right, so we have this thing here, and what I should, before I do this, I should choose just like before, I should choose my C0, so choose C0 such that C0 is bigger than 1, strictly bigger than 1, but yet is strictly smaller than C, right? So you choose this, and now using this, because we have that this limit here converts to C, so it converts to something that is strictly above the C0. This means that there exist capital N such that if little n is bigger than capital N, then the nth root here is bigger than C0, right? But now again, taking the n power on both sides, then you have that an is bigger than, strictly bigger than, in fact, C0 to the n power. But you see these guys here, right? C0 is strictly bigger than 1, so this here actually even goes to infinity, right? So this here does not go to 0. Okay. So this prove again that it's divergent. So this proof 2. Okay. Now the next thing we want to talk about is power series. So power series is, so remember that, so the first example of a power series is something we already looked at, more or less. So suppose that you're looking at the series, some number, I call it x now instead of c, to the power n, and n equal to 0 to infinity, right? Yep. So what we proved, so in the root test here, we proved that the series is absolutely convergent. Here we proved it's divergent, and what we actually proved is we proved that an, in fact, this here an, that is here, allow me to write that it goes to infinity, like this. That they were supposed to go to 0, but we actually, right? If the series was converging, the most elementary thing is, the most basic thing is that the an has to go to 0. Otherwise, it's not going to converge. But in fact, not only do they not go to 0, they actually, in absolute value, goes to infinity. So it's very, very far from being convergent. Right. Okay, so now, so we looked at the geometric series, right? If you think about x as just representing any number, you can look at this series here. This is the geometric series. And we know that it's convergent, so we know that this here is convergent. It's convergent if the absolute value is less than 1, and in that case, this here is, the sum here is just this familiar function. Right? But in general, you may have a sequence, so an, if an, in general, if an is a sequence, then you can form a power series, and the power series is like that, where this is the coefficient. The an is now the coefficient to the x to the power n. Right? So this is, if you will, this is sort of like an infinite polynomial, a polynomial of infinite degree, right? Because the sum of all these polynomials, right? Okay, and this is called a power series. So this is a power series. So this is a power series. And the question is then, the question, which turned out to be quite subtle, is, so a lot of the basic functions can be represented by power series. This here was one example. Another example is another example of, if you're looking at the exponential function, and we'll come back and discuss this more, but the exponential function has a nice power series representation. And this is the exponential function, the power series representation of the exponential function. And also the sine and cosine. So cosine x this also have a power series representation. And the power series is minus 1 to the power n x to the power 2n divided by 2n factorial, where you're summing from 0 to infinity. And sine have a similar one. So sine x has a similar one where you're summing from 0 to infinity, and then it's minus 1 to the power n x to the power 2n plus 1 over 2n plus 1 factorial. And so, and lots of functions has power series representation, but it's not every function. If I write down a function, then, so in fact, it's easy to write down a function that doesn't have. So if you have, but I'm not going to prove to you that it doesn't. So if I take the function that starts off being dead zero, and now it's becoming interesting. So like this function here, this one does not have a power series, even locally does not have a power series. Okay, and the thing is that power series is an example of something that's called an analytic function, and this here is not an analytic function, so that's why I know that it definitely doesn't have a power series. But anyway, so okay, so now right, so the question is that if you take a power series, so suppose you take a sequence an, and you write it down. Suppose you take a sequence an, and then you write down a power series based on it. Then the first question that comes to mind is, when does this, for which x does this series converge? Right? So for which x does this series converge? So this is like the most basic thing. And let's look at some example. Of course, if you look at so the first example, let me just, that is what we already talked about. Suppose I'm looking at this thing here. Well, this here is, x, if you think about x as being fixed, this is a geometric series. And we already know, so this is for each x, for each fixed x, this is the geometric series. So we already know that this thing here converges, so converge for as long as the absolute value sign, absolute value of x is less than 1, and we also know that it and diverge otherwise, right? Because we've already determined that, right? Okay, now you see, like the next example I want to look at is the one power series that represents but we haven't proven that yet, but we'll talk about that next time, is the exponential function. If I'm looking at this power series here, then I'm interested in for what x, for what x does this converge? And so it's natural here to try to apply one of the tests. So you just think about x as being fixed, and you just apply one of the tests. And the natural one is either the root test or the ratio test. Let's do the ratio test. So x as fixed, And I'm not interested in x equal to 0. I'm assuming that x is not equal to 0, because when x is 0, right, this here is just it's only for x to the power 0 is by definition 1. And all the other things all the other terms are 0. Right? So this here it's definitely converging when x is equal to 0. Right? So let's not look at that. And then, because if you don't look at that, you can think about an. You can now think about, as the series where bn is x to the power n over n factorial. If you think about this thing here, and you think about the series as now bn, then the ratio test tells you that if you're looking at the ratio of bn plus 1 over bn, so if you're looking at bn plus 1 over bn, take the absolute value of this here. Well, this is just x to the power n plus 1 over n plus 1 factorial, and then you have to divide it by x to the power n over n factorial. Right, if you do that, this here, right, turns up, flips upside down, and you're getting x to the power n plus 1 times n factorial, and then you're getting x to the n times n plus 1 factorial. So this is what it's equal to. And now, of course, here there are x times itself n plus 1 times. The n of those is canceling out with this, right? So this is x. And here you see here the n plus 1 factorial. You can write as n plus 1 and then times n minus 1, etc. But that's just n factorial. So you can write it like that. And so you see that this here canceled that. So you're left with n plus 1. Remember, x is fixed. If x is fixed as n goes to infinity, this here, for each fixed x, this here just goes to 0. So now you have from the ratio test, if that limit, if it has a limit, it does have a limit. If that limit is strictly less than 1, but it's actually 0, right? So it's definitely falling into under 1, so it's convergent, right? So the ratio test tells you, by the ratio test, this is convergent. Okay? And so we'll finish here. There's a little bit more. I posted already my lecture notes. There's a little bit more, and I'll probably talk about that next time. I'll just start with just talking about the stuff I didn't get to. The stuff I didn't get to was, and we touched upon that earlier, is Leem soup and Leem inf. And the reason why we're covering it here is that what if the ratio, what if these things, what if the nth root, so you're asking for either the ratio or the nth root of something to have a limit. But what if it doesn't have a limit, right? And so it's dealing with that case, okay? All right, any questions?
That means for all x, right? We're saying, like,
this is for all x, but think about x as being fixed. Right? Think about x, you're just asking for one particular x, but it holds for all x. But don't think about x also as being variable, right? Because you think about x as being fixed, and then you let n go to infinity.
Right, and then after you generalize.
Yeah, that's right. And so you have for all x, this makes sense. Right? Then you can ask, how does it vary in x? But that's a different story.